welcome to this module. In this presentation, I am going to share with you the design aspects of microwave filters. A filter is a two-port network used to control the frequency response at a certain point in an RF or microwave system by providing transmission at frequencies within the passband of the filter and attenuation in the stopband of the filter. Typical frequency responses include low pass, high pass, and band reject characteristics. So applications can be found virtually any type of RF or microwave communication, radar, or test measurement system. The development of filter theory and practice began in the years preceding World War II by pioneers such as Mason, Sykes, and Darlington, Fano, Lawson, and Richards. So the image parameter method of filter design was developed in the late 1930s and was useful for low frequency filters in radio and telephony. In the early 1950s, a group of Stanford Research Institute constituting of G. Mathai and L. Young, E. Jones, and S. Stone and others became very active in microwave filter and coupler development. A voluminous handbook on filters and couplers resulted from this work and remains a valuable reference. Today, most microwave filter design is done with sophisticated computer-aided design packages based on the insertion loss method. So, because of the continuing advances in network synthesis and distributed elements, the use of low-temperature superconductors and other new materials, and the incorporation of the active devices in the filter circuits, microwave filter design remains an active research area. Now let us begin our discussion of filter theory and design with the frequency characteristics of periodic structure, which consists of a transmission line or waveguide periodically loaded with the reactive elements. And these structures are of interest in themselves because of their application to slow wave components and traveling wave amplifier design, and also because they exhibit basic passband or stopband responses that lead to image parameter method of filter design. Filters designed using the image parameter method consist of a cascade of simple two-port filter sections to provide the desired cutoff frequencies and attenuation characteristics, but they do not allow the specification of a particular frequency response over complete operating range. Thus, although the procedure is relatively simple, the design of filters by the image parameter method often must be iterated many times to achieve the desired results. A more modern procedure called the insertion loss method uses network synthesis technology to design the filters with a completely specified frequency response. The design is simplified by beginning with the low pass filter prototypes and then that are normalized in terms of impedance and frequency. So transformations are then applied to convert the prototype designs to the desired frequency range and impedance level. Both image parameter and insertion loss methods of filter design lead to circuits using lumped elements because that is capacitors and inductors. And for micro applications, such designs usually must be modified to employ distributed elements consisting of transmission line sections. The Richards transformation and Kuroda identities provide this step. And now let us discuss the periodic structure of filters. An infinite number of transmission line or waveguide periodically loaded with reactive elements is an example of periodic structure. So a periodic structure can take various forms depending upon the transmission line media being used. Often the loading elements are formed as discontinuities in the line itself, but in case they may be modeled as a lumped reactants in shunt on a transmission line. So periodic structures support slow wave propagation and they have passband and stopband characteristics similar to those of the filters. So they find applications in traveling wave tubes, mazes, and phase shifters and antennas. So now let us first consider the propagation characteristics of infinite loaded line. Each unit cell of this line consists of length d and of transmission line with a shunt susceptance across the midpoint of the line, and the susceptance b is normalized to the characteristics impedance, is it not? So if we consider the infinite line as being composed of cascade of identical two-port networks, we can relate the voltages and currents on either side of the nth unit using ABCD matrix. Now let us discuss the filter design by image parameter method. The image parameter method of filter design involves the specification of passband and stopband characteristics for a cascade of simple two-port networks. and so is related to concept of the periodic structure. So the method is relatively simple but has the disadvantage that arbitrary frequency response cannot be incorporated into the design. This is in contrast to the insertion loss method, which is the subject of this. And nevertheless, the image parameter method is useful for simple filters, and it provides a link between the infinite periodic structures and practical filter design. The image parameter method also finds application in solid-state traveling wave amplifier design. Now, let us discuss the image impedances and transfer functions of two-port networks. We begin with the definitions of image impedances and voltage transfer function for an arbitrary reciprocal two-port network, and these results are required for the analysis and design of filters by the image parameter method. Consider the arbitrary two-port network where the network is specified by its ABCD parameters. Note that the reference direction for the current at port 2 has been chosen according to the convention of ABCD parameter. This is shown in this figure. You can see it here. And the image impedances Zi1 and Zi2 are defined for this network as Zi1 is the input impedance at port 1 where port 2 is terminated with Zi2, and Zi2 is the input impedance at port 2 where the port 1 is terminated with Zi1. So thus both ports are matched when terminated in their image impedances. We can derive the expressions for the image impedances in terms of ABCD parameters of the network. The port voltages and currents are related as V1 is equal to A into V2 plus B into I2, and I1 is equal to C into V2 plus D into I2. The input impedance at port 1 with port 2 terminated in Zi2 is given by Zn1 is equal to V1 by I1, that is equal to AV2 plus BI2 divided by CV2 plus DI2, which can be written as A Zi2 plus B divided by C Zi2 plus D, since V2 is equal to Zi2 into I2. So now we can solve the equations for V2 and I2 by inverting the ABCD matrix, and since AD minus BC is equal to 1 for a reciprocal network, we obtain V2 is equal to dV1 minus BI1 and I2 is equal to minus CV1 plus AI1. Then the input impedance at port 2 with port 1 terminated in Zi1 can be found as Zn2 is equal to minus V2 by I2, that is equal to minus dV1 minus BI1 divided by minus CV1 plus AI1. This is equal to dZi1 plus B divided by CZi1 plus A, since V1 is equal to minus Z1 into I1, right? And we desired that Z11 is equal to Zi1 and Zn2 is equal to Zi2, and now these two equations can be solved as Zi1 is into C into Zi2 plus D is equal to A Zi2 plus B. So Zi1 into D minus B is equal to Zi2 into A minus C Zi1. Solving the value for Zi1 and Zi2 gives Zi1 is equal to square root of AB divided by CD, and Zi2 is equal to square root of BD divided by AC. And now consider the voltage transfer function for a two-port network terminated in its image impedances. Then the output voltage can be expressed as V2 is equal to dV1 minus BI1, which can be written as D minus B divided by Zi1 into V1. Now let us discuss about the constant K filter sections. We can now develop the low pass and high pass filter sections, and first consider the T network. And we can see that this is a low pass filter network because the series inductors and shunt capacitors tend to block the high frequency signals while passing low frequency signals. So comparing these results, we have Z1 is equal to J omega L and Z2 is equal to J1 by J omega C. So the image impedance can be written as ZIT is equal to square root of L by C into square root of 1 minus omega square LC by 4, where omega C is equal to 2 divided by root LC. And high pass constant section which is shown in this figure, we see that the positions of the inductors and capacitors are reversed from those in the low pass prototype, and the design equations can be easily shown to be R0 is equal to square root of L by C and WC is equal to 1 by square 2 into root of LC. And next let us discuss about the filter design by insertion loss method. A perfect filter would have zero insertion loss in the passband, infinite attenuation in the stopband, and a linear phase response in the passband. Of course, such filters do not exist in practice, so compromises must be made. Herein lies in the art of the filter design. The insertion loss method, however, allows a high degree of control over the passband and stopband amplitude and phase characteristics with a symmetric way to synthesize the desired response. The necessary design trade-offs can be evaluated to best meet the application requirements. If, for example, a minimum insertion loss is more important, a binomial response could be used. A Sebichev response would satisfy a requirement for the sharpest cutoff. So, if it is possible to sacrifice the attenuation rate, a better phase response can be obtained by using a linear phase refilter design. And this slide shows the characterization by power loss ratio. In the insertion loss method, a filter response is defined by its insertion loss or power loss ratio, which is given by the ratio of the power available from the source to the power available to load. Observe that this quantity is reciprocal of S1 to the whole squared if both load and source are matched. So, insertion loss in dB is given by IL is equal to 10 log of PLR. So, from this we can know that the modulus value of tau of omega the whole squared is an even function of omega. Therefore, it can be expressed as a polynomial in omega squared. Thus, we can write tau of omega the whole squared as m of omega squared divided by m of omega squared plus n of omega squared, where m and n are the real polynomials in omega squared. Substituting these values, the PLR is given by PLR is equal to 1 plus m of omega squared divided by n of omega squared. Thank you.